Hi, I'm Ankit.
I'm Braden.
I'm Kevin.
And I'm Quinn, and welcome to our presentation on autonomous lane keeping and lane changing.
Self-driving cars have slowly grown into the cultural zeitgeist. This is due to the rise of automation, which has impacted various facets of our society. The focus of automation in the car industry is to eliminate human error. As it currently stands, human error accounts for 90% of automobile accidents. In other words, self-driving cars have the potential to make driving safer than ever before. In order for autonomous driving to be successful, lane keeping and lane changing will need to be fully understood and fine-tuned. Systems of lane keeping have existed in the past. Most notably, it was used by Nissan in 2001 on the SEMA 300G, which can be seen in Figure 2 on the right. This system was not nearly as complex as what we have now, or what we will have in the future. It was a simple lane departure warning system that alerted the driver when the car was leaving the lane. This system had no feedback. It simply provided the input into the lane keeping feedback loop, with the output being the driver physically moving the steering wheel themselves. Lane keeping and lane changing are measured on various performance metrics. The metrics are as follows: whether or not there is lane departure, lane changing control for intelligent vehicles, displacement from the middle of the lane, time spent in the desired zone, in this case staying within the lane, and the complexity of the route being taken. Autonomous cars use various forms of feedback. For autonomous lane keeping and lane changing, they use lane keeping support, which automatically keeps the car from veering away from the middle of the lane. There's also a lane departure warning system that alerts the driver if they themselves are driving and don't realize they are veering off-center. Furthermore, the autonomous car is able to recognize road signs and react accordingly. The cars are also able to detect objects in the surroundings and alter their course if need be.
One governing equation of motion is the polynomial approximation of paths being taken. The controller plots a smooth polynomial in which it will try to steer the car into the other lane. This becomes the trajectory the car will follow. This is represented by the graph in the top right corner, which shows a desired polynomial trajectory the car will follow, and the actual polynomial trajectory the car followed. This can also be seen in the animation below, in which the green line shows the car's trajectory as it changes lane. The green line assumes a polynomial path in order for the car to change lanes smoothly. Other governing equations of motion are the sum of forces in the x and y direction, and then the sum of moments in the z direction. In the x direction, the mass times acceleration in the x direction is equal to the mass times the velocity in the x direction times the yaw velocity, which is then added to other forces in the x direction, such as friction, air resistance, etc. In the y direction, the mass times acceleration in the y direction is equal to the mass times the velocity in the y direction times the yaw velocity, which is added to other forces in the y direction. In the z direction, the moment of inertia times the yaw acceleration is equal to the sum of each forces times each of the distances. There are various coordinate frames that are involved in autonomous lane keeping and lane changing. The first frame that is considered is the lane-centered inertial frame. This is the frame that the car is traveling in. In the diagram, this is represented by the axis of y of t and x of t. The next frame is the coordinate frame of the car. The coordinate frame of the car is represented by the rotated x and y axis seen above the car. When the car is traveling along the lane, then this is the frame that is in line with the lane-centered inertial frame. However, when the system turns the steering wheel, it causes a turn angle represented by delta. This rotates the front wheels. The rotation of the front wheels then causes a principal rotation along the z-axis of the coordinate frame of the car into the coordinate frame of the next lane that the car will be changing to. Overall, the change in delta then creates a change in the car angle represented by phi. The change in phi then creates a principal rotation along the z-axis of the lane-centered inertial frame to the frame of the car.
Continuous systems are those that take measurements that are independent of one another, while discrete systems are those that file the values taken into discrete categories. The measurements taken from the vehicle to the boundary of the lane are continuous measurements, but for the purpose of lane keeping, it is sufficient to break all those measurements into discrete categories if the vehicle is within a certain distance from the edge of the lane or whether the vehicle is outside of the lane. The purpose of lane keeping technology is to maintain current position within a lane. Thus, the total amount of data that could be gathered by a vehicle's myriad of sensors would be greatly more than required for this singular task. For the purpose of lane changing, the measurements can be organized as continuous as the system is in a transient state, requiring more measurements which are not able to fit into as simple categories as before. Lane changing goes beyond the realm of simply maintaining position in a given lane and approaches more autonomous functionality. So an increase in the amount of data gathered and that data's precision is necessary.
There are many inputs that are factored into automatic lane keeping and lane changing. In the visible spectrum, regular cameras surround the vehicle in order to measure the lane markings, which are then used to provide position data about the car. The image on the top right is an example of such a camera that is used to measure the lane markings. Radar is used to measure the speed of the vehicle and distances of vehicles and/or objects around the car. Radar is used because it can operate at a much longer distance than the regular cameras. A range of ultrasonic sensors are utilized for their high accuracy at short ranges, to fill in the gaps left by other sensors. Additional inputs include internal gyroscopes, electronic compasses, and GPS information that give the vehicle its spatial coordinates. The image at the bottom is a visual representation of how all these sensors are used to provide information all around the car.
The raw measured inputs mentioned in the previous slides are converted into more mathematical figures used in the positioning and steering of the car. One of the most important things done with the car's positional information is the generation of a desired path for the car to travel along. This path can be lane-centered when driving down the freeway, or it can be a polynomial path generated by the onboard computer for the purpose of lane changing. Some of these specific inputs pulled from the raw data include the lateral position, which can be with respect to the lane or with respect to the desired path, the lateral velocity and acceleration, the yaw or the angle of the car with respect to the lane, and the car's speed, a vital piece of information when calculating a polynomial lane change. All of these inputs get fed into the control laws of the system in order to determine the appropriate turning output for the vehicle. Now that the inputs of the system have been gathered and converted into simplified system properties, mainly the distance diverged from the desired path, these inputs are used to determine the output of the system. In the case of an autonomous vehicle, steering. Steering, however, directly affects the inputs of the autonomous vehicle system, creating a cyclical aspect to the system, where input causes output and vice versa. This is called a feedback loop, specifically in the case of lane keeping, a negative feedback loop. A negative feedback loop is where the output of the system is designed to counteract the input. For example, veering left from the desired path will cause the vehicle to turn right, thus returning to the desired path. In short, this is what happens when an autonomous vehicle makes lane keeping decisions. However, it's not as simple as discrete left or right control system. How sharp to turn and for how long is a very complex field called the control laws. One of the simplest control laws would be a proportional control unit, where rate of turn is proportional to the displacement from the desired path. Proportional control is great for demonstration of a control law. However, it does not react fast enough or accurately enough to be used in real-life autonomous driving. This is the job of the PID controller. A proportional integral derivative controller, or a PID controller, is the industry standard system of control laws used to keep a dynamical system in the desired equilibrium. PID controllers are very versatile as they are highly adjustable. With a PID controller, the response time and accuracy can easily be tuned to fit a given system. The PID controllers do this by giving different weights to each of the three control units: the proportional unit, which makes simple corrections proportional to the amount of divergence from the desired equilibrium. The integral unit eliminates steady-state errors, but it tends to increase overshoot of the target equilibrium point. And the derivative component quickens the response of large inertial systems and weakens the tendency to overshoot.
Legacy companies throughout the automotive industry have begun to implement automatic lane assistance as well as adaptive cruise control in most mid to high tier vehicles available in the United States. Companies have specifically risen up around this technology, such as Waymo and Uber, who operated limited automated taxi service in designated areas of the country. Tesla uses its fleet of vehicles to gather data while providing driver assistance. The current cars produced include an array of sensors, as can be seen in the animation on the bottom of the screen, that allow semi-autonomous functionality while gathering vast amounts of data to be analyzed and used to develop future, fully self-driving software. The seeds of the future can be seen in the automobiles of today, as modern car makers begin to utilize both autonomy as well as producing vehicles with higher fuel efficiencies and a move towards electrification. The automotive industry has embraced the semi-autonomous and fully autonomous future that is coming. Most companies have projects dedicated to automating certain aspects of driving, such as lane and speed control, while others have embraced full autonomy. Companies like Waymo and Tesla are working towards putting fully autonomous vehicles on the road in the near future. Many institutions have begun thinking of how a fully autonomous future would affect infrastructure, such as a possible signalless interchange seen in the animation below. Many laws and regulations must be written and amended to allow for such a future, but as the technology matures, it seems difficult to expect an alternative. An increase in autonomy could lead to a drastic decrease in traffic accidents that would otherwise be caused by human error. Such is the end goal of self-driving technology.
Thanks for